Good morning from Germany. I think we can start now. Welcome to our webinar. I am very happy how many participants are online with us today. It is amazing. My name is Victoria and I am your host today. So before we start, just a few remarks for your information. Please feel free to type in any questions that come up during the webinar in our question box. We will answer as many questions as possible at the end of the webinar. And if there are too many questions, don't worry, we will answer each question via email within the next days. If there are any technical problems, please don't worry. This webinar is being recorded and you will automatically receive a recording of the webinar within the next 2 days by email. Well, now I would like to introduce you to our today's speaker, Dr. Elena Mukina. Elena studied physics and mathematics at the Yaroslav State University in Russia and has a PhD in physics. She has been part of the NETCH analyzing and testing family for over 20 years now and has gained lots of experience in our R&D department before taking over the position of the business field manager for the software Kinetics Neo last year. Elena has been a huge contribution to the development of the Kinetics Neo software, which she will demonstrate today. So welcome, Elena. We are happy to have you here today talking about polymer crystallization behavior. I will now hand over to you to get started. So enjoy our webinar and have fun. Thank you.
So, good morning, everybody. I'm here. I think you hear me. And today I start our webinar, Polymer Crystallization Behavior, Easy Understanding by means of Kinetics Neo software. And we have 4 points. The first one is target of crystallization analysis. The second is isothermal crystallization. We'll speak about different analysis method and how to select the necessary analysis method for isothermal crystallization. Next one is non-isothermal crystallization, again with analysis method and selection of methods. And number 4 is advantages and limitations of different model and method for simulation. First, why crystallization kinetic is necessary. If we speak about kinetics, then usually we have some transformation A to B. For chemical kinetics, it's a reactant goes to product. For crystallization, we have melt and then it goes to crystal or crystalline in the case of polymers. There are 2 purposes of kinetic analysis. The first is pure academic, where crystallization mechanism is a subject of study. Here, target is to find and describe kinetic mechanism of crystallization, to see what are intermediate type of crystals, are there some competing between growth of different type of crystals, and what is the final crystal. And industrial purpose is happens if crystallization mechanism is unknown or not important. Here we can predict crystallization rate and degree of crystallinity for given temperature program and optimize industrial process, decrease production time and costs, and improve the quality of product. If you speak about crystallization, for example, crystallization of polymer, then during crystallization, some energy is produced, some heat energy, and we can measure this energy by differential scanning calorimetry. In this case, we have an instrument. We have 2 crucibles. One of them has material, and we make heating and cooling for this material and see what energy or what is heat flow in this instrument. For example, for crystallization, we usually make cooling and material goes from liquid state to crystalline state, and we see a peak. This peak means a heat flow inside material. We can make slow heating, slow cooling or fast cooling. For fast cooling, crystallization is more intensive and heat flow is more intensive and the peak is much higher, but it has some moving to later time because we have some delay and because the crystallization process is kinetic process and depends on time as well. If we see polymer for heating, then usually we can observe three thermal effects. First is the glass transition, where a mixture of glass and crystalline has some step. And here the glass, the amorphous part of polymer has a step in heat capacity. Then we have a mixture of elastic amorphous and crystalline. After that, we have cold crystallization or recrystallization, where crystalline part will crystallize, where amorphous part will crystallize. And after that, the crystalline has melting and we have a liquid polymer. During cooling, we have only crystallization. After crystallization, there is a mixture of crystalline and amorphous part. And after that, the amorphous part has a glass transition again, and we have a glassy state and crystalline state. Now we will speak about a transformation or about crystallization from melt to crystalline. If you speak about kinetic, then we must have a property in the current time state. So if we have time, we have heat flow as a peak, we have a total peak area, and we have a current peak area. Then there is a value which called alpha or degree of conversion, which is the ratio between current peak area to the total peak area. And this value of conversion shows us degree of crystallization. At the beginning, it is 0. At the end, it is 1 because everything is crystallized. But sometimes during crystallization of polymers, crystallization is not complete. Then the final value is not 1, but less than 1. If you have a first derivative of conversion, then we have some equation which shows crystallization rate. And this crystallization rate has three parts. The first is just normal pre-exponential factor. A second part depends on the current conversion, depends on the current degree of crystallization. And the last one, K of T, is dependence on temperature. Dependence on conversion, usually in literature used as Avrami nucleation. Here is some equation which shows how the nuclei are produced in our polymer, how fast it's produced. Another possibility to make, to calculate the number of nuclei is Shostak-Berggren equation. So Shostak-Berggren has a little difference from Avrami because Shostak-Berggren equation has more degree of freedom. It has a couple of additional parameters. For dependence on temperature, there are again many possibilities. The first, the simplest one, is Arrhenius dependence. It's the same like for chemical reactions. And another one is non-Arrhenius dependence. And here in Kinetics Neo, we use for non-Arrhenius dependence Hofmann-Lorentz theory. Here we speak about model-based analysis. But additionally, there are a model-free analysis, model-free kinetic for crystallization. And here is everything very simplified. Here only Arrhenius with activation energy. Here always a reaction of the first order and pre-exponential factor has dependence on alpha. And now we will speak where which model could be used and where we recommend to use each of these models. Firstly, how to work with these models in Kinetics Neo. Firstly, we have DSC instruments. A DSC instrument makes some measurement with different curves, different peaks. Then we load these peaks into software, into Kinetics Neo software, and make processing of it. Processing means that we remove baseline and recalculate to degree of conversion. After that, for several curves, we apply kinetic modeling or kinetic method, and we can create one model which describe one model, all of this data. So we don't have 4 models, we have only one model. And here we can use the modeling for fitting, for example, Avrami, Nakamura, Hofmann-Lauritsen, or we can use model-free kinetics, doesn't matter. As we have one model for all experimental data for different temperature conditions, then we can use this model for predictions and simulations. For example, predictions at different temperature conditions, either thermal, dynamic, or arbitrary. We can predict degree of crystallinity, crystallization rate. We can make optimization, for example, to find temperature for constant crystallization rate, or to find temperature profile for given crystallization profile as well. And now how it works in details. Firstly is isothermal crystallization. Let's take polyamide 12 and a measurement at 164 degrees C. Here we have a DSC with exit down according to our standards, and here is exothermal peak with direction down, and we can recalculate conversion, and we see that at the end it is 1, and it has some exponential exponential curve which goes to 1. In order to describe this curve, usually the Avrami equation is used, where degree of conversion, this is alpha, is calculated as 1 minus exponent from time, and time has some power. This is the nucleation, dimension of nucleation, and some constant. Additionally, we can calculate a first derivative. First derivative is our heat flow, or just proportional to our heat flow, and again here is a function of degree of conversion, and additionally k. If we apply this mathematic to one curve, then we have a model which works for one curve only. So we cannot use this model for other temperatures, because our experiment has only one curve, and it means that the model which is based on one curve works for one curve only. If we would like to have one model which works at different temperature, then we must have several experiments at different temperatures. For example, here from 162 to 168, then we recalculate to conversion, and we see that it is the same Avrami nucleation equation, but K is a function of temperature. It is different for different curves. And this function of temperature is decreasing function. Now is the question, where can we take this function of temperature? How could we describe this function of temperature? And the easiest way, very easiest way, just to use Arrhenius dependence for this function of temperature with activation energy. Usually very often in literature, this happens because Arrhenius is well known for chemical reaction, and it is very easy to apply the same mathematics for crystallization. Let's try and see what happens. Inside our kinetic snare, there are several methods and models according to Arrhenius. Here, STM 2070 method A, Friedman numerical optimization for everything for isothermal crystallization, and for model-based Avrami, Shostak-Peregrine, Avrami with different nucleation dimension. Here we have activation energy. If we speak about activation energy for chemical reactions, then for chemical reaction, activation energy has a real physical or chemical sense. It's energetic barrier, and a molecule must jump over this barrier in order to react. And usually the higher temperature, the faster chemical reactions. And here is everything normally. Activation energy is positive and it has sense. But if we apply the same mathematics for crystallization, then we have very some strange things for understanding. Here, for crystallization, the crystallization rate is higher for lower temperature because we have supercooling. And if we apply Arrhenius kinetic, then activation energy is negative. It means that a reaction goes slow with increasing of temperature. It's the first point, and the second point, this value of activation energy is just apparent value. It has no any physical and chemical background. And this approach works really in very small range, just below melting temperature. Let's try to apply. Firstly, model 3, STM 2070. We see points are experimental data, lines are our model, and according to this method, you can find activation energy, but you see the fit is really not good. And from my point of view, I ask you really not only to find activation energy, but always check if the fit okay or not okay, because sometimes in literature only the values, the final values are published, but we cannot say if this value is okay or not okay, because no any fit is present, and we cannot say yes, okay or not, it is not okay. Here in this case, we try to make a fit and we see immediately this is not okay. But model 3 Friedman works well. Here is very good agreement between experiment and our simulation. Numerical, it's our NECH method works well as well. Model-based has also very good fit. So it seems that Arrhenius approach works for model 3 and for model-based methods, and there could be good fit. Now we can compare results with model summary. And here we see that statistically, for example, numerical, Friedman, Avrami, and I just stressed Shostak-Berggren have almost the same results, the same good result. And STM has very high value sum of deviation squares and cannot be used. F-test is really high. The question what to use here, if the values 0.99 for everything, then they are statistically good, and F-test is also good. And usually we should select a model with a less value of degree of freedom. In this case, it's Avrami. It has less number of parameter for fit, and we recommend to use Avrami method. And if we have one Avrami method, then we can use this model with Avrami reaction type for simulation. For example, we can make a simulation of signal here at different temperature, which were not in our experimental feed. In experimental data, we can make conversion. We can make predictions for time of half crystallization, where degree of conversion 0.5. Here we have the time in hours and the temperature, inverse temperature. And for Arrhenius approach, it is straight line. In this case, everything works well. And the problem, this, not the problem, but we should take into account that it works only for very small temperature range, for temperature range where experiments were done. And here a couple of additional examples. Here LDPE, low density polyethylene, in our laboratory was done a couple of isothermal measurement. We have again Avrami with perfect fit, and we can make predictions. And for the higher temperature, the lower crystallization rate. It's normal because of supercooling. Here is PP, polypropylene, again, several measurement, isothermal measurement, Avrami reaction type, perfect fit, and we can make predictions. So it seems that Arrhenius approach works well for isothermal conditions. It has very good advantage. It is very simple, very fast. The mathematics of chemical reactions is used here for Arrhenius approach, but it has a lot of disadvantages. First disadvantage, this Arrhenius approach, Arrhenius means dependence of temperature with activation energy. Arrhenius approach has no physical background. The activation energy is just apparent and negative value, usually negative value. This method does not take into account diffusion near glass transition temperature. You cannot use this method for predictions what happens near glass transition temperature because there is no any information in this model. And this method works only for very small temperature range near melting point, nothing more. And outside of this range, it produces incorrect predictions. Conclusion, this approach is very simplified, has very limited working temperature. Let's go back to our picture for heating and cooling. Here we have a glass transition temperature and melting temperature. And if I speak about melting temperature, it's not a maximum temperature, it's equilibrium melting temperature. And there is some special technique to find it, but now we just think about that there is some melting temperature. And for isothermal crystallization, usually we have experimental data just before, somewhere before melting, below melting temperature, and simulation range for Arrhenius approach works only at this temperature. If we try to apply this model somewhere here or here, then it doesn't work. Or it works, it calculates some results, but these results are wrong. And please take into account that if you use, for example, model-free kinetics for isothermal crystallization, then it works only in the temperature range where experiments were done. And you cannot go outside of this range in any case. What to do if we would like to go outside of this range? In this case, we must not use isothermal crystallization, we should use non-isothermal crystallization. For example, PET, polyethylene terephthalate, is a material for plastic bottles, for example, for cola. And here are some experimental data which are done in our laboratory. And cooling was done with cooling rate from 1 K per minute to 10 K per minute. And if we speak to peak area, then for 1 K per minute, it's 38 joule per gram. And for 10 K per minute, it's not 38, it's only 2 joule per gram, 2.5. Why? Because for very fast cooling, there is no time to make complete crystallization. Temperature goes down to glass transition, and then everything is stopped and nothing happens anymore. Here we have, of course, we can try Arrhenius approach for non-isothermal data, and see what happens. Here we have some Arrhenius approach for non-isothermal data. It was done for chemical reactions, but we can try. Let's see. It doesn't work at all. If we apply Azawa-Flynn-Wall model-free analysis, we see the lines are not parallel. Here, vertically is log of heating or cooling rate, and horizontally is 1 divided by absolute temperature. And if you see the fit, we see that the experimental data and our simulated data are not in agreement with each other. We can try another model-free, which was very good for isothermal things, for isothermal data, but it doesn't work at all. Friedman not work, Kissinger not work. We can try to use model-based. Avrami doesn't work. Shostak-Berggren doesn't work at all. Why? If we have here glass transition and melting temperature, then we have Arrhenius approach, which works somewhere here, but our crystallization happens here. So there is no any chance that Arrhenius will work here for our crystallization data in very wide temperature range. What to do? We should find another approach, non-Arrhenius approach. And this non-Arrhenius approach in Kinetics Neo use Hofmann-Lauritsen theory, and it works from the point T infinity, which is 30 degrees below glass transition. And here, if you see on the curve, then the glass transition is the middle of the step on the DSC curve, and T infinity is the point where nothing happens, you see. And here at this point, T infinity is no any viscous movement happens, and there is nothing here. Therefore, for Hofmann-Lauritsen, the not Tg, but T infinity is used. And the upper temperature is melting temperature. For Hofmann-Lauritsen theory, we have again our crystallization rate equation. For dependence on degree of conversion, we use Avrami. For temperature, we use Hofmann-Lauritsen. It has two parts. The first part is diffusion term. It depends on T infinity, and this T infinity is 30 degrees below glass transition, and at this temperature is no any viscous flow. The second part describe the behavior near melting point. It is a nucleation term. It has delta T. Delta T is a supercooling. It's a difference between melting temperature and the current temperature of material. This method works in the total temperature range between T infinity and the melting. If we see the picture, then we have diffusion term. This diffusion term has very low values near glass transition range, and in this range, the blue curve is the sum of this. We have range 1, where crystallization range increase with temperature. Second is nucleation term. Nucleation term here, the gray one, it has very small value near melting point, and here we have another range where crystallization rate decrease with temperature. And now we can try to use this blue curve. Curve is a sum of diffusion and nucleation. This is K of T from Hofmann-Lauritsen theory. We applied and we have a really perfect result for PET. And it described not only the shape, it described also the difference in the areas for different heating and for different cooling rates. If we make conversion, predictions of conversion, then we see when something happens. And for example, for PET, during production of the plastic bottle, there is a stretch blow molding is used, and during stretch blow molding, there is a very, very fast cooling. And after that, material must be stay about 1 hour at the temperatures between 110, 120. We did here the simulation up to 150 and see what happens with material. The idea to keep material transparent, to keep material in glassy state, and to have no any crystallization. Because if material has some crystallization inside, then our plastic bottle will not be transparent, and it is really not very nice optically. Let's see here for our simulation at temperature, for example, 120 degrees C here. We see that for very small temperature, almost no crystallization happens. And for temperature at 140 or 150, here we have a lot of crystalline inside and materials. Our bottle is not transparent anymore. Next very interesting thing is just to compare heating and cooling, or just compare experiment for the complex temperature program. Inside Kinetics Neo software, there is a possibility to make predictions of crystallization, not only isothermally, not only for constant cooling, but really for complex temperature program. For example, we can make a simulation for a temperature program which has two steps. One is cooling with 3 K per minute and another is heating with 10 K per minute. And we can see that the part of crystallization happens during the cooling, but it is not complete because we just come to glass transition range and have high diffusion. And a second part happens during heating. Here we have two parts, and during heating, what happens during heating depends on previous history, depends on the cooling rate before. If we show the same data for temperature axis, then we have two peaks. One is big one for cooling, minus 3 K per minute, and another is small one with heating with 3 K per minute. And now let's compare this with experiment. Here are our experiment. We have firstly cooling, we have crystallization peak, and after that we have some small isothermal stabilization segment, and then heating, and there is again the crystallization peak. We can show both peaks over temperature, and we see first peak is big one and a second peak which is smaller and a little bit probably twice smaller and has a little bit moving to the higher temperature. What exists here and does not exist in our simulation is a melting peak. Here is a melting peak. Here is the beginning of the melting peak. It exists in experiment but does not exist in our simulation because our simulation is only for crystallization, not for melting. And we have no experimental data of melting in our model, and therefore for simulation there is no predictions of melting. What's very interesting here, if you make isothermal lifetime predictions, then we see at different temperatures. For example, for a range between 110 to 220 degrees C, then we see that crystallization has, for PET, has the highest rate somewhere at isothermal conditions with 170 degrees C. And somewhere on the first and on the near glass transition and near melting temperature, we have very, very slow crystallization and very long time for predictions, very long isothermal time for 20, 50, and 80% of conversion. Here is the next point is PBT. Probably last example. Here we have cooling, and for cooling, we have data. We can try to apply Avrami, the same as it was before, and which works very well for PET. Avrami plus Hofmann-Lauritsen. And you see here we have no very good agreement. But if we use not Avrami for the first part, but instead of this we use Shestak-Berggren, then the fit is really very, very nice. So here, this problem, which happens with Avrami, with Nakamura, where Avrami and Hofmann-Lauritsen is used, happens not only for PBT, but for any other polymers. And I was really unhappy because of this, because everywhere in literature only Nakamura is used. And a couple of months ago, I just got a proposal from colleagues from France, here. And here was the idea to use, instead of Avrami nucleation, the Shestak-Berggren crystallization, and then everything works well. And I'm really happy about this. Here, if you compare the results, the equations, then we see the same logarithmic term for nucleation. Then we see the term for first order for Avrami and nth order for Shostak-Bergren, and additionally here some kind of nucleation. So it means that for PBT, crystallization is a little bit more complex than the normal Avrami. And here we can make predictions, for example, for cooling. And what's interesting, that for low heating rate, crystallization complete, and for fast heating rate, crystallization, it's cooling from higher temperature to lower temperature. We see that crystallization is not complete because we just go to diffusion range. Predictions and simulations. Again, here in kinetics, we have nucleation and Shostak-Bergren for f of a in our kinetics NEO software. And for temperature dependence, we have Arrhenius approach and non-Arrhenius approach. Important, Arrhenius approach is partial solution which we recommend only for isothermal crystallization. But what's important, this solution works in very small temperature range, just below melting temperature. We do not recommend to use this Arrhenius approach, also including model-free kinetics for non-isothermal conditions and for other temperature ranges. And another is non-Arrhenius approach with Hofmann-Lauritsen theory. This works for both isothermal and cooling crystallization, and it works for complete crystallization range. Again, working range for Arrhenius and non-Arrhenius approach. Here is Arrhenius approach near melting temperature. Non-Arrhenius approach for Hofmann-Lauritsen approach is between T-infinity and melting temperature. In kinetics NEO, for model base, there are 4 different possibilities. The first of them is Avrami for conversion and Arrhenius for temperature called AN. Second one, Shostak-Bergren and Arrhenius called SB, and it works only for isothermal crystallization and small temperature range. Second one is non-Arrhenius approach, Hofmann-Lauritsen and Avrami nucleation. Inside kinetics software, it's called Nakamura reaction type, and you can use it for both isothermal and cooling crystallization. And the same is for Shostak-Bergren crystallization, where Shostak-Bergren and Hofmann-Lauritsen theory is used. And another one is model-free kinetics. Yeah, it's very simplified, and validity of this method is really not very high. And now I would like to make a short presentation of software, how it works. Here, I think you see the software now. We have isothermal data for PA12, polyamide 12. The data are for different temperatures. And here we can apply Arrhenius kinetics, for example, Friedmann. Here we have vertically log of reaction rate, horizontally 1 divided by absolute temperature, and this is fit. Fit is really very well, and R square is 0.998. It's really good. We can use model-based kinetic, which is based also on Arrhenius. Here we select Avrami. So Avrami reaction type, make fit, and then the simulated data have a good agreement with our data. These both reactions, now we have only 2 of them, have Arrhenius approach, and they work only, we can make a simulation only in very, very small range. But we can use here also non-Arrhenius approach, a Hofmann-Lauritsen. We can just add, for example, Nakamura crystallization. Here is Nakamura. We put here a melting temperature, for example, 185, and the glass transition temperature from experiments. And after that, we can make optimization and see what happens. Now we see Nakamura results here again, 0.R² is 0.998, and here this model works also for all temperature range. Let's see how it works. We can go to isothermal lifetime and see that for Nakamura predictions, I just switch off and have only half-time crystallization for 0.5 degree of conversion. Here for Nakamura, we have total range between 50 and 180 degrees C temperature. We can just put here, for example, 220. Doesn't matter, it works as well. Here, and Nakamura works for total temperature range. But if we select, for example, Avrami, then we see it works only for half temperature range. And it works only for melting, near melting temperature. Here we have 1 divided by temperature, by absolute temperature, and it means that the left part is a melting temperature and right part is temperature near glass transition, and for right part is no any predictions. So this model doesn't work for temperatures a little bit more far from the melting range. We can select model-free kinetic, for example, Friedman, and we see that it doesn't work for right part, doesn't work for glass transition as well. And now I would like to open PBT data. Here we have our melting, our cooling data during cooling from 230 to 150. Here we will not use Arrhenius approach. We will firstly try Avrami plus Hofmann-Lauritsen. It's Nakamura. So here select Nakamura crystallization. For Nakamura crystallization, we must manually put a temperature for melting and temperature for glass transition because the software must know it. Here we put melting temperature and glass transition temperature and make optimization. We see that Nakamura does not work well because here we have experimental data and fit, and it is not very well somewhere here. Another model is Shestak-Berggren crystallization. Here, signal, we select Shestak-Berggren crystallization. Here again, we must put a melting temperature and crystallization temperature. Yes, and then we can start optimization. So during optimization, glass transition temperature will not be optimized, but a melting temperature will be optimized a little bit. And now we have a really perfect fit for Shestak-Berggren crystallization, which contains this Shestak-Berggren crystallization contains Shestak-Berggren equation for conversion and Hofmann-Lauritsen for theory. And I'm really very happy about this. And of course, you can make isothermal lifetime and put it from glass transition to melting temperature. And you see it works well. We can make dynamic for different cooling rates. We can just put here everything. We can make multi-step predictions for several segments. If you want, you can make some kind of climatic predictions. We must just switch to time and select on the map some point, and then you can see how crystallization happens for some material which is stay on the climatic conditions. And if you have in your production very big machine, then we can just select external temperature profile, and if you have your data as a temperature versus time as a function, temperature versus time, then you can just load this data, arbitrary data, and see how crystallization goes for your data. That's all. here, and few small slides here are some literature which was used during development on this part of Kinetics Neo. Here we have ICTAC kinetic recommendations, which contain crystallization kinetic, and this crystallization kinetic is used in our Kinetics software. We have kineticsnatch.com website where we have all information about all versions. We have very good training part. You can just go here and try step by step, try to learn step by step on the data which are pre-installed. Here there's a possibility to have a trial version of the software for 30 days, and there are some user guide training examples, and if you have some comments, then there is a possibility to put your comments on this software. And finally, Kinetics Neo works not only for crystallization, it works for chemical reactions as well. We have a lot of model-free methods and model-based method with unlimited number of reaction steps and kinetic models. We have some special reaction types like Nakamura, Hofmann-Lauritsen, Kamal-Suror, and it works very interesting for predictions of curing, including T-T diagram and taking into account glass diffusion control and glass transition. And I would like to tell you that in 1 month, I mean exactly in 1 month, on 23rd of March, we have next webinar, and it will be for kinetics for polymers. And here it will be not only crystallization, but the decomposition and curing reactions and time temperature transition diagrams and so on. Probably it will be interesting for some of you. And finally, I would like to thank you for all my colleagues from laboratory, Stefan Schmölzer, Claire Strasser, and Natalia Rodolph, who prepare data for this webinar. Thank you, and your questions.
Okay, thank you, Elena, for this great presentation. I can already see a few questions. I would just start reading them, and then we can try to answer them. The first question, one of our attendees is a PhD student in polymers for 3D printing applications. And she is interested if there is a free edition of Kinetics Neo for students or universities. Elena, you already mentioned the free trial version, and how is it for universities?
So firstly, the kinetics can be used for 3D printing, and we have some application examples which will be shown in May. And here for universities, firstly, we do not sell it for students, we sell it for universities, and university is half of the price of the normal price for the first version of Kinetics, and any additional license has only very reduced price. But in any case, it should be goes from university, or of course PhD student can go work with this, and you must speak about exact price with your local representative, and then you will get price in your local currency with taxes and local taxes and all other things. So you can find a list of your local representative on Netch website, or you can just ask, write me or write us, and we will tell you who is your local representative. Yeah. Next one.
Yeah, perfect. Thank you. Next question. Please, could you advise the best way to start learning kinetics basics for beginners? For example, how to use crystallization tests will support us in quality control and research and developments of polymers, compounds such as PVC, PE, and PP. Advising the best way to start learning kinetics.
So firstly, I could recommend to use our training part in our website. I think it is somewhere here. It's Learn. So here now we have only one crystallization example with Nakamura. You can just go step by step. And if it's not enough, then you can order the training in Netch by Netch Academy. And then you can get the complete training course for some hours or some days. And after that, you will be able to work very well with Kinetics Neo. But I think here, usually for very simple examples like it was shown now, it's enough to have a couple of clicks and then you are inside.
Okay, perfect.
Next one.
Thank you. Another question, maybe two questions from the same person. First question, is there limitations in cooling rate modeling? Example given up to 400K per minute?
Yeah, in any case. In any case, so usually we recommend to make predictions not too far from experimental data where this model is created. So if you have some data for 5, 10, 20, maybe 50K per minute, then we can usually make predictions to 100, maybe, yeah, just a little bit more with factor 2, factor maybe 3 sometimes, but not more. Of course, in any case, it should not be about 1000K per minute. And this is a first thing. And a second thing which should be mentioned here, for very high, for experimental data with very high heating and cooling rate, the time constant of instrument has plays some roles, and then the time constant of instrument should be removed from the data. And in this case, Kinetics Neo contain the functionality to make deconvolution and to remove time constant. So if your instrument can make 100K per minute, then please use it. Then remove influence of time constant, so make deconvolution, and then you can make predictions up to 200K per minute, maybe 300K per minute. But I will not recommend to go extrapolation to higher cooling rates.
Okay, thank you. Next question. Can you put in raw data from DSC equipment, from example given TA, instruments and PerkinElmer?
No any problem. And here on our website, there is information in FAQ, I think, section somewhere here, how to import non-Netch data, and we have already experience with PerkinElmer data and the instrument data. It's no any problem.
Okay, thank you.
And we have experience with data from other instruments, not only this two.
Okay. Next question, could you tell again the date for the second webinar for kinetics of polymers in March? You already mentioned it. It's the 2nd of March, I think.
No, it is exactly in 1 month. Yeah. So today is 23rd of February, and the next one is on 23rd of March.
Yes, and you can keep in touch on our webinar overview website. It's netch.com/webinars. Every planned webinar is online there. Okay, so the next question. One question. You said that with increasing the heating rate, there are decreases, but how you choose the area in the NeoKinetic software? Should not all curves have the same area in the software? Question mark.
No, these depends on the method. So next webinar, I will show this exactly. So if you speak about model-free methods, then yes, it is according to methods, the area must be the same. But if you speak about model-based method, the model which are based on the theory, for example, like here, then the original data must not have the same area. And you have already shown here, you have already see here the PET example, polyethylene terephthalate. And here for 1 K per minute, it was 38 joule per gram. And for 1 K per minute, it was only 2.5 K per gram. And sorry, joule per gram. And the areas was totally different, and it was not a measurement error, it was a really physical law, and all this data are inside modeling, and there is no any problem to make a modeling for this data with Kinetics Neo. It's with model-based method, it is possible, and it is normal, it's okay, it's correct.
Then the next question, do you choose the same baseline for all of your curves or just choose the baseline in order to get the same area under the curve?
Depends on. Here we have something like this. I just switch to, yeah, it's time. We go from right to left, but here we have some experimental data. Here is, we have 49 for, here is again 49, here is again 49. So here the experiment have 49 and this one is 48. So here the experiment is done that they are in agreement with each other. So if physically it should be the same, then usually no. So it depends on experiment. So if the problem with different areas comes from physics, for example, like for PET, then we just select the baseline with different area. We cannot select 2.5 joule per gram for all data, because for one is 2, for another is 30. It's really measured and it will be different. And for other experiments, according to physics or chemistry, it should be the same, but it depends on the selection baseline. And then we should select baseline in order to have more or less similar area. So it depends on the physics and chemistry of your material. For one cases, it must be different, and they are different. For other cases, they must be the same, and we select to have the same. Depends on.
Okay, thank you for the great answer. The next question, what will be the subject of the session 2 today, or is it the same again? Maybe I can answer this question. It will be exactly the same presentation again, just for the other time zones of the world. So feel free maybe to participate. Thank you, Elena, for your time and the webinar. I would say we can come to an end now. Thank you for all of your questions and participation. Just for your information, we will keep in touch via email and answer the open questions for you the next days, as I already said. And of course, you get the recording of the webinar. Thank you for your time.
Yeah, thank you. Bye.
Bye. Thank you.